All right, welcome to this explainer. Today, we're diving into a really fascinating, almost invisible high-stakes battle that's happening right under our noses on the railway. We're talking about the clash between massive, raw railway electrification and incredibly delicate control electronics. Think about it for a second. A modern electric train is just an absolute beast of pure power, right? Yet, it's completely controlled by digital systems that are incredibly fragile. So how exactly do these two extremes coexist without frying everything? Well, let's dive into this engineering puzzle.
Here's our roadmap for today. We'll be hitting 5 key areas: high-voltage traction systems, electromagnetic interference, immunizing the railway, SCADA control systems, and finally, uninterruptible power supplies. Let's just jump right in.
Okay, part 1, high-voltage traction systems. To really get why this is such a problem, we first have to establish the sheer mind-boggling scale of the power required to move hundreds of tons of metal at high speeds. We're definitely not talking about the kind of power you use to charge your laptop here. We are dealing with immense industrial-scale electrical forces that fundamentally alter the physical environment around them.
So, the central engineering question we have to answer is this: how can highly sensitive digital control systems operate just inches away from 25,000 volts of raw power? I mean, these trains can draw currents of around 300 amps straight from an overhead catenary wire right down through the rails. It creates a wildly, incredibly electrically noisy environment. And honestly, this perfectly illustrates the core conflict. On one hand, you've got traction currents. They're massive, they're powerful, and they are incredibly messy, just completely filled with harmonic distortion from the train's motors. But then, on the other hand, you've got our signaling and telecommunication cables running right alongside those same tracks, carrying vital safety data that strictly requires absolute quiet. Imagine trying to have a whispered phone conversation while standing front row at a heavy metal concert. Yeah, that is exactly the kind of environment our signaling cables are forced to endure every single day.
Which brings us to Section 2, Electromagnetic Interference. This conflict between loud power and quiet data leads to an invisible war happening along every single mile of electrified track. We call it electromagnetic interference, or EMI.
You see, modern high-speed electric trains draw massive currents, and those currents create incredibly powerful electromagnetic fields. These fields literally threaten to drown out the vital data that's keeping those very trains from crashing into each other. Because the traction return current flows right through the running rails, any parallel signaling and telecom cables are basically sitting right in the middle of a giant magnetic field.
So what does this interference actually do in the real world? Well, traction currents flowing through overhead lines or third rails induce hazardous voltages and crippling noise into those nearby cables, creating a whole host of serious safety hazards. For starters, it can inject terrible noise into speech circuits. Imagine a train driver trying to radio control in an emergency and only hearing deafening static. Even worse, it can actually corrupt data, which might trick a track circuit into showing a false clear. That means the system tells the computer a section of track is totally empty, when, in reality, a train is sitting right there. And of course, on top of all that, it creates very real, very dangerous shock hazards for the engineering staff working on the lines.
All right, moving to Section 3, immunizing the railway. Now that we understand just how big of a threat EMI is, let's look at the primary engineering defense used to protect the network. Because look, if we can't get rid of the electrical noise from the trains, we have to make our equipment somehow ignore it. This brings us to a really brilliant concept called immunization. It basically ensures that our delicate equipment can distinguish its own vital control signals from the roaring harmonics of the traction current. We are essentially teaching our equipment to only listen to a very, very specific language and completely tune out the electrical shouting going on all around it.
Engineers use some incredibly clever workarounds to pull this off. For instance, they'll operate track circuits at very specific, kind of weird AC frequencies, like exactly 83.33 Hertz. Why? Because that specific frequency simply doesn't exist in the traction power's harmonic spectrum, so the equipment can easily tune out the noise. They also use physical defenses, like balanced twisted pair cables to actively cancel out noise, and they install these big booster transformers on overhead lines to literally suck the return current out of the rails and into a separate wire, keeping it far away from our data cables. But lately, the ultimate solution is migrating entirely to fiber optic cables. Since they use light instead of electricity, they're totally immune to magnetic fields, ensuring things run safely no matter how much power is surging overhead.
And the tech keeps having to evolve, because modern three-phase traction drives create such complex interference across a massive range of frequencies, it's getting way too hard to find an electrical frequency that the trains aren't already drowning out. So there's a huge shift toward heavily shielded equipment, like axle counters. Instead of relying on electrical circuits in the rails, these systems just physically count the train's wheels as they pass by. It's a much more robust solution for today's superpowered railways.
Okay, Section 4, SCADA control systems. Once the track level is fully secured against all that interference, we need to zoom out to the macro level to see the systems that are actually monitoring this electrified battlefield. We need a secure way to manage all this power from miles away. Enter SCADA. SCADA acts as the all-seeing overseer. It relies on highly available super-secure data links to monitor the health of the entire high-voltage network. Without SCADA, trying to manage the electricity for hundreds of miles of track would be, well, completely impossible.
From central control rooms, human operators use these SCADA interfaces to constantly evaluate power flows and instantly detect any dangerous faults in real time. Say a tree falls on an overhead line, or there's a massive short circuit. This system sees the voltage drop immediately. But for this to actually work, the telecommunication links carrying the SCADA data must be absolutely bulletproof against the very interference we were just talking about.
Because when an emergency does strike, SCADA allows operators to follow a really precise sequential process to safely and remotely isolate the traction power from a specific section of the railway. They detect the fault, they use those robust voice networks to quickly verify the issue with drivers or track workers, and then, boom, they hit a button to cut the power. It's a critical safety net, but again, it relies entirely on flawless data transmission.
Finally, Section 5, uninterruptible power supplies. This brings us to the ultimate fail-safe question for our entire control network. What happens to our all-seeing overseer and all our vital safety signals if the lights completely go out?
If the main utility grid fails, and, power cuts do happen, we absolutely cannot afford to lose our critical signaling and telecom networks. I mean, just imagine dozens of high-speed trains running blindly in the dark with no signals and absolutely no way to talk to control. It's a completely unacceptable risk.
So, to prevent those kinds of catastrophic failures, signaling and telecom systems are completely isolated onto their own dedicated, conditioned power networks. This ensures absolute stability. They don't just plug these critical systems into the local city grid and hope for the best. They require power that is heavily regulated.
So how do we engineer this kind of rock-solid stability? We protect both the equipment and the staff through comprehensive earthing, heavy insulated units, and meticulously smoothed DC supplies. And that smoothing part is absolutely vital, because any electrical ripple in the DC power supply can actually transfer straight into the telecom equipment and cause deafening audio noise on the emergency telephones. We have to scrub the power clean. And to guarantee that vital communication lines, like those emergency phones right at the control desk, never go dead during a blackout, the entire setup is backed up by uninterruptible power supplies, or UPS. These control centers are literally the brain of the railway, and a UPS ensures that the brain never loses consciousness, even for a millisecond.
A UPS system acts instantly. It uses massive battery backups to bridge the gap and keep the control center fully alive while alternative supplies, like backup generators or the traction network itself, kick in. The key here is zero latency. The computers don't reboot, the phone lines don't drop, the batteries just silently carry the load until the secondary feeds take over. It's totally seamless. Which leaves us with a pretty fascinating thought. As we push for faster and more powerful railways, drawing more and more current, how will our engineering continue to evolve to protect the ever-increasing flow of delicate digital data from these massive forces of electrification? We are constantly pushing the absolute limits of physics here, balancing raw megawatts of power on one side with the fragile gigabytes of data required to control it safely on the other. It's a never-ending arms race of engineering, and honestly, it's exactly what keeps the modern world moving safely. Thanks so much for joining me on this explainer today. I really hope it sparked your curiosity.